Okay, folks, continuation of section 3.4 in the chain rule, but I want to just work a few more examples here. In the previous video, which was kind of lengthy, we did a lot with the notation. We worked through some examples, which was essentially a polynomial plugged inside another polynomial or inside a power function. Um, those are good. Let's look at a few other examples involving the e function. Let's do that. So let's say I've got a function. We've seen something like this. Let's say I've got 5 e to the x. And then now let's introduce something like this. Let's say I've got e to the 5x. And let's discuss the difference between these two things. Okay, so for this function f, this is really a constant multiple. So this rule goes back to section 3.1. We could have done this stuff once we established that we know the derivative of e to the x. This is just a constant times a function, and this is a basic function, one that we know its derivative. It's not something we have to find or calculate. We just know the derivative. So here, f prime of x, step by step, if we want to show the constant multiple rule in action, it's what we're doing here. To take the derivative of a constant times e to the x is 5 times the derivative of the e to the x. Right, so that step shows me setting up how my derivative is going to work, but I haven't actually differentiated my e to the x. But then final answer is 5. Derivative of e to the x is e to the x. Okay, so we already know the derivative of e to the x. We use that here. The derivative of e to the x is itself. And now we see that if you've got a constant times e to the x, then the derivative of that function is also itself. Right, because the e to the x produces its own derivative. The constant comes through for the ride as our constant multiple. Good. So we had that. We didn't use the chain rule right there. All we used was we knew the derivative of e to the x, and we used the constant multiple to pull it out, and that's it. Okay, so that was not a chain rule exercise. This thing, we need to use the chain rule. Okay, why do we need to use the chain rule here? So if you try to set this up, I already called it g. I could call this something like a capital F like we did in the previous video. And you could try to set up what your outside and inside functions are, right? There's sort of a special, I'll kind of explain the chain rule in the context of exponential functions. It's nice to see sort of its own rule written that way. But what I'm thinking is for exponential functions, the exponent is the inside function. Okay, in other words, I can express here g of originally a function of x. I can write it as e to the u, right, if u is equal to 5x, right? So I'm kind of maybe say it the other way, let u equal 5x, and then my original function here is e to the u, all right? Then the way I want to take the derivative of that is g prime with respect to x is going to be first the derivative of my function with respect to u, and then times u prime. So what I'm really doing here is the derivative with respect to u of e to the u times the derivative of u with respect to x. Okay, looks a little hairy, maybe looks a little complicated. That's really just our chain rule, though. What we saw in the previous video, we used the letter y to represent this. So if we said here y was e to the 5x, but then we said here y is e to the u, right? When we made our little substitution of u equaling 5x. So just make that note. And then what we want to find is the derivative of y, right? Y prime, which was dy dx. And the way to do that, though, was to use the intermediate, right? dy dx, we wanted to do dy du, and then multiply that by du dx, okay? So here, since y is e to the u, though, if I wrote d du, this first derivative d du of y is e to the u, right? And then times du dx, and that's what I've written over here. Okay, so getting a little, I'm interchanging a lot my different notations, right? What I'm calling these different things. I'm calling it g, I'm calling it y, it is e to the u, right? So it's got plenty of different names, but that's the idea. Okay, so let's finish up this derivative. So we know the basic derivative of e to the x, right? I know that derivative with respect to x of e to the x is e to the x, right? That means if I've got an original exponential function, this base e raised to the exponent x, then if I take the derivative with respect to that exponent, I get itself, right? But there's nothing special about that exponent or that variable x, right? If I had e to the t, if t was my variable, but I took the derivative with respect to t, then I would get e to the t, right? So sometimes they use the phrase dummy variable, not meaning a dumb variable, but more like a mannequin, a dummy, right? It's like a placeholder. It doesn't really matter what we call that, right? If I call that variable, I could have e to the happy face. So you can invent your own math symbols if you want. I could have e to the happy face. If I take the derivative with respect of e to the happy face with respect to that variable happy face, I get out an e to the happy face, right? So silly examples, but what that means is we already know this. The derivative of e to the u with respect to u is itself, right? Is e to the u. Just like the derivative of e to the x is itself, e to the x. Multiply that by now the derivative of u with respect to x. So if you want to write that out on the side somewhere, solve that, you can find it. If you just want to figure it out now, u is 5x, so du dx is just that constant of 5. And you can double check that using some power rules or using whatever, but we just get the constant 5 right there. All right, so that derivative, the inside derivative, or the derivative of the exponent is a 5. And then, as always, though, we want to finalize our final answer by, we want to get the u out of there. We want to go back to terms of x. So this e to the u was e to the 5x, right? And now a 5 appeared out front. Or it appeared on the back, but I would probably write it out front and write 5e to the 5x as my final answer. All right. So I erased that original function f that we had that first example, but actually that function was the derivative of this function. Okay. So it's pretty simple. It produces itself. So the things that we want to happen do happen. E to some exponent, right? Since the derivative of e to the x is itself, the derivative of e to the 5x is itself, but then also times the inside derivative, or sometimes they call the upstairs derivative in this case. All right, we multiply by that exponent. And that's it. All right, let's do another couple with e. And then maybe we'll do a crazy one with some trig stuff. So, one way to write this is the derivative with respect to x of e to the u. So this is a way of actually writing the chain rule for specifically this function e to the e. The derivative of with respect to x of e to the u is e to the u times du dx. And if you like it, you can call it like that, or you could say e to the u times u prime, right? Because u prime is the same as that, so a little bit cleaner. So yeah, so kind of just itself produces itself times the upstairs derivative, or the derivative of the exponent. And that's it. So that's our nice little sort of formal chain rule for this particular function. Before I go further, because I don't think I mentioned it when we covered exponentials, all we've done so far is the derivative of e to the x, right? We did not do the derivative of other bases, and it's not itself. It's related to that, but then some logs appear, so we're going to get there eventually once we get to derivatives of logs. But all we've done so far is e to the x, just to clear that up. Let's say I've got this function, f of x is e to the x cubed, right? So last time I just had 5x, a nice linear exponent. Now I've got a cubic up there. So that looks even more complicated. But let's see if we can just get this out quickly. My function is f, so I'm finding its derivative f prime. Remember, the derivative of e to something produced a copy of itself. So we're going to get a copy of e to whatever that thing is, right? Times the derivative of that thing. That's it. Times d dx of x cubed. That's it, right? What's the derivative of x cubed? 3x squared. Usually the convention is pull those things, the x's and the stuff in front of the e. So the derivative of this, 3x squared times e to the x cubed. And there we go. That's it. That's our derivative. Okay. What if you wanted to take the second derivative, right? What if I wanted to now take f double prime? And if we haven't seen this before, f double prime is really just f prime, right? So it's the derivative of the derivative. We call it the second derivative. Could you go further? Yeah, what would you have to use? A couple things, right? Now you've got a product here. You've got x, the 3 is a constant, so that guy's going to come through. But you got x squared, and then you've got e to the x cubed, right? So you'd have to use the product rule. So part of the product rule is you'll have this, and part of the product rule, when you take the derivative of this thing, right, that's what we did earlier. So that means when you take the derivative of this thing, this whole thing is gonna like pop out again. So it kind of like spawns itself. It's kind of weird the way these E things work. If you take further derivatives, this thing will sort of keep replicating, but with other terms. So I'm not gonna do it right now. Maybe play with it for fun. Could be fun. But yeah, that's it. Okay, couple of examples. Let me do a sort of triple nested example. Let's see if we can figure this out. So let's say I've got f of x is sine of cosine of tangent of x. That's of s, right? Do I have I was looking at those parentheses. Do I have enough? Tangent of x is my very inside function. That function is being plugged into a cosine function. So cosine of the tangent of x, and then whatever that value, that function, is getting plugged into a sine, right? So this is sort of like a double chain rule, right? Or a composition of three functions all combined, all plugged into one another. Notice it's not multiplication. It's not this, sine of x, and then parentheses, cosine of x, parentheses, tan of x. That actually looks a little weird with those parentheses, but then it's not cosine of x and sine of x. It's cosine of tangent of x, right? So we really do have those compositions here. So, different styles to do this. Could you start labeling u and v? Sometimes you might want to introduce and make a whole bunch of side work. Maybe. Let's try to just work through it. So a lot of these rules, I try to just dive in, work through the process. Hopefully, it works out nice, but I'm still going to kind of go step by step. So, think back to what we did. I had something to the eighth, right? I had some poly earlier, our first example. And we kind of did it we kind of mixed and matched our steps. But when we found the derivative, part of it was what I call the outside derivative. So we started from the outside. The most outer thing on the outside of these parentheses was the 8 as an exponent. And we said, well, if I have an 8 as an exponent, then I think that should happen. The derivative of this thing to the 8th should happen, right? That was our outside derivative. So I'm going to start on the outside and kind of work in. In other words, the derivative with respect to x of sine of x, we know, is cosine of x, right? We saw that in class together. So the derivative of sine of x is cosine of x. That means if you've got sine of u, and you take the derivative with respect to u, then you get cosine of u. All right? And u, we interpret as not just a variable like x, we interpret as of u as a function of x, or as a function of other things, right? So here u is this entire inside. U is the cosine of tangent of x, right? But as far as I'm concerned, it's just the inside of, or the argument of the sine, okay? So sine of something, the derivative of that is going to be cosine of the something. But then, since we have a chain rule, we'll have to multiply that by the derivative of the inside and keep working inside, and keep working deeper and deeper, okay? So step by step, the derivative here is going to be cosine. I just had an idea. Sine of cosine of tangent of x. So I'll try to color code those. I don't know how visible all those colors are to you at home, but got blue, got purple, got black right there. Okay, so the derivative of sine of something is cosine of something. Boom. Derivative of sine of something is cosine of something. Then we've got to multiply that by, though, the derivative of the rest of that piece with respect to x. And so derivative with respect to x of the inside piece, which is cosine of tan of x. There we go. Okay, so that's like sort of step one, sort of unwrapping the layers, if you will, of this derivative. Okay, so I started with sine of some complicated piece, but I know the derivative of sine is cosine. So the derivative of this composition is going to be cosine of this entire thing, cosine of tan x. I fill that back in, right? So that's like my u sitting there, times now the derivative of the inside derivative. Okay. Believe it or not, now this piece is actually, we're done with that. In other words, we took the derivative of sine, we got cosine, we've got those terms in there. This piece is part of our answer. And now, but we've got to go further, we've got to differentiate this thing, right? We've got to take the derivative with respect to x of this, which means embarking on another chain rule, okay? So what we're looking at, though, is, I wonder if doing all these colors is crazy here. I wonder if it's helpful. Got that right there. Okay, so this thing was my ultimate outside derivative, all because of that sign right there. And now I'm multiplying by the derivative with respect to x of cosine of u, right? That's what I'm really thinking of right now. So now in the side, I'm thinking the derivative with respect to x of cosine of x. We covered that in class. We discussed it. We said it's negative sine of x. Okay. So if I have cosine of just a simple variable x, then its derivative is the minus sine of x. If I have cosine of something more complicated, something like a u, some other function, but if I take derivative with respect to that u, then I just get minus sine of that u, right? And that's it. Okay, so in other words, the derivative of cosine of something is going to give me minus sine of that something. Okay, and I have the habit of leaving those parentheses blank just for like a moment, so kind of like breathe and remind myself. So I have cosine of something, I took the derivative of that, and I got negative sine of something, times, because that something is itself a function of x, we have to continue the chain rule. So the derivative of this composition is negative sine of that something times the derivative of that something. So times d dx of tangent of x. Okay, so we've still got one more derivative to take. So in the first step here, we're kind of like peeling off the layers of an onion. In the first step, we had this outer layer of sine, and we kind of peeled that off into its derivative and said, well, that sine just produces a cosine of whatever's inside. Okay, and then the next layer, then we're here, right? This derivative, that's like, we want to peel off the next layer. So now the next layer under there is a cosine. And we said, okay, I can peel that cosine out and take its derivative minus sine of whatever's inside, right? Of that little core of the onion that's left over, which is this little tangent. And then finally, we've been taking the derivative. So the derivative is sort of moving through the original function. Now it's to the very inside piece. And so now we don't need a chain rule anymore. We just take the derivative, or we know the derivative of tangent of x, and we're all done. Okay, so just to fill in the details here, we had cosine of something. So its derivative was negative sine of something. So tan x lives there. And now I've got one more step to take the derivative of tangent of x. Okay? What could I do right now? On the board, I could just erase that, right? Erase that and replace it with this derivative to save some time. And especially since I did this in all the crazy colors, that might seem prudent. But let me just write it out. Let me see if I can kind of write this out a little bit. Cosine of tan of x times that minus sign I'll probably pull out front. Let me do that now. Let's pull this minus sign way up front, because that's just a minus 1, right? That negative sign is just a negative 1 being multiplied by something somewhere, so maybe pull it way out front. And then what I've got left here is times sine of tangent of x. All right, and now finally, what's the derivative of tangent of x? That's going to give me a secant squared of x. There we go. That's it. So that's just my derivative. We looked at that using a quotient rule in class together, but that's one of our basic trig derivatives that we would want to try to recognize. Okay. So now this minus 1, if you don't like that, again, you could go back to like a negative sign, however you want to represent that. There's some kind of negation going on here. Is there anything I can clean up with this now? No, not really. And so you might be saying, well, here, secant is 1 over cosine, right? So I've got 1 over cosine squared of x. So I've got cosines in the denominator, I've got cosines in the numerator. Can I somehow cancel if I convert that secant over? But you can't. We can't cancel. And the reason is because this cosine, or this secant rather, and then this cosine is a function of just x. This cosine, though, is not a function of x, right? So in other words, if you have cosine of x over cosine of x, you can cancel those because those are the same thing. But if you have cosine of tangent of x, that's a different function than cosine of x, right? Those inputs are different, so there's no cancellation. So no reason to do any kind of simplification. So leave it like that. Okay. I wanted to do one like this because I think there's one like this in the homework. So kind of just an exercise. If you can get through this, you can get through a lot. Just go step by step, right? Think of that onion metaphor, right? Just one layer at a time. Works out well.